Evolutionary algorithms are optimization and search techniques inspired by the principles of natural selection and genetics. If you think about it, they're kind of the other half of artificial intelligence, in that if you want to look to nature to find a paradigm to solve problems, you have the brain and you have the process of evolution. The brain is already mimicked by things like reinforcement learning or deep learning, and for evolution, we have evolutionary algorithms. These, of course, rely on the Darwinian principle of selection of the fittest. You start by generating a population, you subject it to a challenge, and you select the ones that best perform this challenge, and you create the next generation based on their traits. So the environment here is what is called the fitness function, which actually gives a score to the solutions to measure how well they perform based on the objectives of the problem that you're trying to solve. Our goal is to maximize fitness, and we will use Darwinian selection to do that. The way this works is fairly simple. We generate a bunch of random solutions, we take the best ones, and then we subject them to changes. And hopefully we will generate a few better ones in this process. And you do that with variation operators. So this could be something like mutation, crossover, recombination, all of which I will get into later. The aim of this library, as it was designed, is to provide an easy to use and intuitive framework to build your genetic algorithms with. So it should make it easy to build different architectures and processes of evolutionary algorithms. And you should be able to tailor your program to the problem that you want to solve, without writing a whole bunch of new code every time. The classical applications of evolutionary algorithms that are usually listed are things like the knapsack problem or traveling salesman, or if you want to look at something that is more realistic in that it is used more in real life, there's the classroom scheduling or the antenna design problems. But they've also been used to examine evolution itself, to study the process of natural selection. For example, in studies examining how certain pressures lead to the appearance of certain traits. Like in this paper, for example, where they looked at risk aversity as a trait, and they found that it is an adaptation to living in smaller groups. This is because in the experiment they ran, they found that when a small group takes a risk and it doesn't pay off or it harms them in some way, the smaller group takes a very large hit from that and their lineage may die off because of it. Whereas a large group can take a risk and then it can take the hit from the risk. And they found that when they limited the group sizes of their artificial populations, these smaller groups were much less likely to evolve risk-taking habits. So this is to show that evolutionary algorithms are not just artificial intelligence. They're also a tool to study the biological process of evolution. But their most common application is as artificial intelligence, so in problem solving. Evolutionary algorithms, they especially excel in situations where the solution space is complex, whether that's because there's multiple local optimums. In these cases, deep learning tends to get stuck on local optimums. For instance, in the classroom scheduling problem, the goal is to assign classrooms to courses while minimizing the class overlap, because if you have overlap then students cannot go. But there's also constraints like the capacities of classrooms and the times of teaching. You don't want a lecture to be too long, whether students are available, whether teachers are available. So this is a combinatorial optimization problem that has lots of local optima. Compared to something like deep learning, it is actually easier to make an evolutionary algorithm fulfill multiple conditions, maximize for multiple things, and in fact, generate multiple solutions as well. Because by their very nature, genetic algorithms have a population they are working with. So starting, the first thing you need to do while using this program is actually set the parameters for your population. The population takes several variables. The first one is population size, which is simply the amount of individuals that is in your population, and this will be kept as a constant. As bad solutions are removed, the new ones are being put in. Your next variable is the number of chromosomes. A chromosome is a self-contained unit consisting of a bunch of genes. And you can have it so that your entire genome is one chromosome, so it's in a single piece. Or you can have multiple. And if you have more than one chromosome, this allows you to perform different operations. I will describe this later. Next variable is the number of genes. This is simply the number of genes that are found in a single chromosome. So here you see two genomes, and you will notice that these are different. One of these has 64 genes in 8 chromosomes, and the other one actually has 8 genes in one chromosome. But more importantly, one of these has genes ranging from 0 to 64 and the other just has zeros or ones. This is because of the representation variable. And depending on whether you've chosen either integer or binary representation, you can choose to specify a couple more parameters, such as the number of positives variable. You can see here that we have a chromosome size of 8 and a number of positives of 1. That means that in a chromosome we will have 7 negatives and 1 positive, so 7 zeros and 1 1. And when you're using integer representation, you have 2 variables that go with it. One of these is gene range. This is simply the range that your integers can take place in. If you say 0 to 100, your gene values will be from 0 to 100, and then you have no overlap. This makes it so that this chromosome will not have the same integer value twice. In the case of our chess problem here, this allows us to not place queens on the same tile. So this is a setting that you can use in, for example, combinatorial problems. For some problems you may use a binary space representation, and for others you may use integer. And in fact, in some problems you can use either or. For example, here in the 8 queens problem, you have a 64 square 8 by 8 regular chessboard, and you want to place 8 queens on it, but in a way that none of them are threatening each other. And here are a couple examples, one of them using the binary representation method and the other using integer representation. In a way they're kind of the same in that both of them have the phenotype of a chessboard. These genes express a chessboard. However, because of the differences in how these genotypes are actually handled, one of these is actually the better kind of representation for our problem that we are solving. And you can imagine that for different kinds of problems, you have different kinds of representations that are more advantageous. For this problem, the number of positives variable is actually really advantageous. So we expect the binary representation to work better, because it allows us to add the rule that one line must have one queen. And after that, it only needs to figure out that one column and one diagonal has to have one queen. So we're starting ahead by virtue of our representation, because the binary representation actually takes the variable that we can have one positive per one chromosome. And since one chromosome represents one line here, this means that one line will only have one queen. We are representing the same problem in different ways, and this will inevitably have an effect on how efficiently our algorithm will solve this problem. So that's representation, or as it's sometimes called, phenotyping. Phenotype is another biological concept that refers to the observable traits of an individual. So in humans this could be height or blood type and things like this. And here we have our genotype, which is this list that you're seeing here, these numbers. And our phenotype is the chessboard that is generated as a result. And writing the phenotype part of the code is also up to the user. This is not something that can be given to you by the library. This is problem dependent, just like the fitness function, and it's something you have to write for yourself. So when you're generating the population, you need to design your representation, and when you're doing the training run, you need to design the fitness function. Other than these two, the library takes care of it. And once you got your population, you can actually start training. The training function gives two outputs, the fitness history and the cost history. Fitness is how well your individual actually performs the fitness function, the challenge. And cost is, well, the opposite. It's the negative of the fitness. So you start training. The first thing you pass is the fitness function, as you described. The fitness function in our case just checks the lines, the columns, and the diagonals to see if there's another queen that collides with the current one. The second thing you pass is the number of generations for which the training will run. Obviously, the longer you have this, the better solutions you will generate, because the evolutionary process will have run for longer. It's rather straightforward. And then you have selection pressure. So selection pressure is actually a variable that determines, in the current version, what percent of the best performing candidates will make up 80% of your new generations. So if in this generation we are generating 100 new solutions, 80 of those solutions will be picked from the top 10% of our population, and the remaining 90% of our population will actually generate the 80%. This is a way to increase diversity. If you have more selection pressure, you will have more elitism, and if you have less of it, you will have more diversity within your population. But the most important ways of generating diversity are what are called variation operators. These are what's responsible for taking a genome and then turning it into another. The first one we have is called mutation. It's controlled by the mutation rate variable, the rate at which an individual chromosome will undergo a mutation. Mutations have different types. They can be a swap, meaning one gene is replaced with another, or they can be uniform, meaning, especially in integers, you will change the values of an entire segment of the chromosome. The mutation strength variable here determines how much of a chromosome will actually undergo mutation. And then you have crossing over, or crossover as it's defined here, which is actually another biological concept which refers to the exchange of segments of genomes between two chromosomes. And the advantage of that is that if you have a couple genes that work well together, they are exchanged wholesale to another chromosome. What this does is it doesn't disturb an already existing and well-working solution. You can pass things wholesale. And in biology, usually, genes that function together or that work well together are physically close on the chromosome. The distance between them is short, and this means that they are more likely to be crossed over together. You have a couple types. One of them is single point. This will just select a point from the chromosome and it will exchange everything after that point with what is found on the other chromosome. So you're exchanging segments. And then you have ordered crossover, which is something you use in combination problems if you don't want to have overlaps. Then you have recombination. This is a little bit different from crossover because what it does is that it doesn't change the content of the chromosome, but rather it swaps chromosomes between individuals. And every one of your chromosomes in this program actually has an index. So you have 1, 2, 3 as it goes. Just like how in biology you have different types of chromosomes and you inherit one from each of your parents. You have 23 types of chromosomes and you inherit one from each of your parents, so you get 46. And importantly, there will not be a case where the X chromosome you get from your mother is replaced by, for example, chromosome 6 from your father. And this function mixes up the genomes, the chromosomes, in a way that it respects the type of the chromosomes. This is useful when you created a kind of representation where each of the chromosomes have a specific duty, like in how in humans we have sex gametes, so X and Y chromosomes. And the design purpose of this variation operator is that it respects that. So if the way that you design your algorithm doesn't require type-dependent genes, you can actually even skip recombination, and you can even make it so that your whole genome is represented by one chromosome. Because then you don't need to segment it if there is no different types of chromosomes responsible for different things. And the last variation operator that I've implemented as of now is the scrambling. This is actually a bit of cheating because nothing like this exists in biology. But, well, the power of evolutionary algorithms is that you're just using the principle of Darwinian selection. You're not actually bound by the rules of genetics as they exist in nature. And what this does is it splits your chromosome into a certain amount of pieces depending on the strength that you have set, and then it will randomly reassemble these. So it's kind of like crossover in the sense that it's made to preserve solutions that work well together. So those are the variation operators. They are responsible for creating diversity, but you also need to have ways of maintaining diversity. And for that we have a couple more things happening in the training loop. Diversity is important to have a more efficient problem solving process, and in the more extreme cases of low diversity, you need to have a way to prevent duplicates or very closely related genomes from clogging up your population. So this is an interesting thing that sometimes happens. In mathematics they would say that you are getting stuck at a local optimum, but in terms of biology it actually reminds me of the Richard Dawkins argument of the selfish gene. So a solution appears, it's generated by your variation operators, and it's actually better than other solutions, so it makes its way to the top. The problem is that this is a bit of a genetic dead end. There is no easy way to turn it into something better, because evolution works on gradual improvement rather than on large leaps. If you have a genome that cannot be readily improved by mutation or recombination in as few steps as possible, so in a naive implementation of a genetic algorithm, it can happen that this individual will keep copying itself and it will clog up your system, because as more and more copies of this is being generated, it's replacing the other genomes in your population. other genomes which might potentially yield better results in the future. So as it keeps copying itself, it actually kills the diversity of your population. And it's actually in line with evolutionary theories. In a sense, it confirms some of these ideas. In particular, the selfish gene argument of Richard Dawkins, which says that the beneficiary of the process of evolution is actually the gene itself. According to the gene, there is no problem to be solved. All the gene wants to do is to spread itself. So when you're implementing a genetic algorithm, you're thinking, well, I will use this to optimize the results of my problem. But the gene is just thinking, well, I just want to spread myself. So you're fighting against the problem and the challenges that it presents, but you're also fighting against the gene itself, in a way. In order to prevent this, you use things like roulette wheel selection, or you can call it stochastic selection. Here in the current version that I've implemented, you have a selection pressure variable. So let's say you have a population of 100 and a replacement rate of 0.3. That means 30% of your population will be replaced and renewed every generation. And if you have a selection pressure of 0.05, that means 80% of your newly generated individuals will come from the top 5% of your population, fitness-wise. And the remaining 20% of your generations will actually come from the remainder 95%. You can increase selection pressure to have more elitism, or you can have it lower to have more diversity within your population. And then there's the fitness function. This is something that you have to write yourself if you want to use genetic algorithms to solve something, because the fitness function is actually problem dependent. So depending on what your problem is, you need to come up with your own fitness function. And then you pass your fitness function into the training loop. I made it this way so that for one training run, you use one fitness function. And essentially, that means you put all the population through this condition, the fitness function, for one run. But you can also make it so that you can retrain the same population with a different fitness function. If you want to take your evolution in one direction and then in another direction. So that's the code as it is now. The code will probably change. I have certain things in mind that I will add, but the general idea will remain the same. This is a customizable way of designing your genetic algorithm, your evolutionary algorithm. Of course, you can play around with it. I've included two problems that are commonly used with genetic algorithms: the traveling salesman problem and the 8 queens problem. And the fitness functions for these are already defined, so you can play around with it. So that's it. That's the code as it exists now. That's the release version. If you have any suggestions, if you have anything that you would like to see, if you have any questions, you can ask them. I will make another video just to make it really clear how it works. I will look at the two problems that I've defined, the 8 queens problem and the traveling salesman problem, and you can see how it works. So that's it for now.